Hey everyone, and welcome to The Explainer. Today, we're diving into something super fascinating, the hidden computers that run our everyday lives. We're going to peel back the plastic and metal to truly understand the invisible machines working silently in the background. It's an incredible journey, going from the macro devices we interact with every single day, right down to the microscopic logic that powers them. Okay, let's dive into this macro to micro roadmap. First, we'll meet the embedded system. 2, anatomy of the system. 3, the processor, which is the brain. 4, microprocessors versus microcontrollers. And finally, 5, peripherals, the senses and limbs. Section 1, meet the embedded system, hidden in plain sight. Think for a second about the complex devices you interact with daily. They're absolutely everywhere, operating right under our noses. For example, an ATM. It's a massive, highly complex machine, right? But it is entirely dedicated to a very specialized set of financial operations. Because it's completely encapsulated by the device it controls and dedicated to just that predefined task, it's a prime example of an embedded system out in the real world. Or take Tesla's superchargers. Even the simple act of delivering power requires complex, hidden computing systems. There are invisible electronics housed right inside those charging stations. They have to communicate with the car, regulate the voltage, and ensure safety protocols are met in real time. Now, flip to the complete opposite end of the size spectrum. We've got the smartwatch. It encapsulates an entire computing universe within this tiny, tightly constrained form factor. It just sits right there on your wrist, tracking time, monitoring health metrics, communicating with your phone, all from a highly optimized, miniaturized package. So, how do we actually define what we're looking at here? Well, a standard system is just an arrangement where all the units work together according to a fixed plan, kind of like a mechanical watch showing the time. But an embedded system, that is specifically a microcontroller or microprocessor-based hardware system with dedicated software embedded right inside it, designed for a specific task. Think of a fire alarm. It has literally one job, detecting fire, and it relies entirely on embedded computing to do that flawlessly. Section 2, anatomy of the system, building blocks. Let's shift our focus inward and look at the exact DNA of these specialized devices. Every embedded system generally relies on 3 main components. You've got the physical hardware, the application software, which acts as the patterns of zeros and ones telling that hardware what to do, and often an RTOS, or real-time operating system, which schedules tasks and controls latencies. But what really defines them are their characteristics. They're single functions. I mean, a pager always acts as a pager. They are tightly constrained, meaning engineers have to heavily optimize them for cost, physical size, and power consumption. And finally, they are reactive and real-time. A car's cruise controller, for instance, absolutely must react instantly to the environment without any delay. And this brilliantly illustrates the whole setup. Right at the center of this conceptual design is the controller, the brain. This hidden intelligence takes instructions, receives information from input peripherals like buttons or sensors, and then dictates actions to output peripherals like LEDs or motors. As users, we rarely even realize this brain is there. Section 3, the processor, the brain. Let's zoom further in from the general system layout right into the central intelligence of the machine itself. The processor is the absolute heart of an embedded system, and it has a biological heartbeat of its own known as the instruction cycle. It involves 2 essential units, the program flow control unit and the execution unit. Together, they continuously cycle through 3 steps. First, they fetch the instruction from memory. Second, they decode what that instruction means. And third, the execution unit, which includes the arithmetic and logical unit, will execute the calculation or operation. Once finished, the cycle immediately repeats. It's a constant loop. But how does this brain organize the memory it fetches from? Well, there are 2 distinct architectures. The von Neumann architecture utilizes a single shared memory space for both program instructions and data. While it's simpler, it actually limits operating bandwidth because the system has to take turns accessing data and instructions. On the flip side, the Harvard architecture splits these into 2 completely separate memory spaces. This dramatically improves operating bandwidth and even allows for different bus widths, making it highly efficient. Section 4, microprocessors versus microcontrollers. This brings us to a critical distinction in the embedded world between 2 incredibly important, yet very different types of brains. What's really interesting about this is the contrast. A microprocessor is multitasking in nature, like the CPU in your laptop that lets you listen to music while you type. But to work, it requires external memory, like RAM and ROM.
That makes the overall system heavier, costlier, and definitely more power-hungry. A microcontroller, however, is single-task-oriented. It has all its RAM, ROM, and timers embedded together right on a single chip. It is the ultimate, lightweight, low-power tool explicitly designed for dedicated embedded tasks.
Section 5. Peripherals, senses, and limbs.
An isolated brain really can't do much on its own, right? So we need to transition to how this controller actually touches, sees, and speaks to the physical world using peripherals. And sure, GPIO pins. That stands for General Purpose Input and Output, and they are the direct lines of communication. These tiny metallic pins coming out of the microchip are configured by the system as inputs to read external voltages or as outputs to send a voltage of 0 or 1 out into the world. They are literally the fundamental bridge between the digital brain and the physical hardware.
Another absolutely crucial internal peripheral is the timer. Because time governs everything in an embedded system, from blinking LEDs to sampling data. Timers operate independently from the main processor in two main modes. In one-time mode, it acts exactly like a stopwatch, counting down to 0, interrupting the core processor to say, hey, time's up, and then disabling itself. In periodic mode, it counts down, notifies the core, and then automatically reloads to do it all over again, creating a steady, repeating rhythm.
Now, as we all know, the real world is messy and analog, but our brain only understands digital numbers. That's where our conversion peripherals come in to save the day. The ADC, or analog to digital converter, takes real-world analog signals, like a temperature reading, and converts them into a clean digital integer that the processor can actually understand. Conversely, the DAC, or digital to analog converter, takes digital data from the processor and smoothes it out into an analog signal to drive things like audio speakers or AC motors.
You can really see the stark difference here between a purely digital wave with its jagged, quantized steps of zeros and ones, and a smooth, continuous analog wave that represents the physical environment. These differing waves prove exactly why ADCs and DACs are absolutely mandatory. A digital brain simply cannot survive in an analog world without them translating.
Of course, sometimes brains need to talk to other brains. Serial communication is how data is transferred one bit at a time between devices. UART, which stands for Universal Asynchronous Receiver Transmitter, is the standard here. It's elegantly simple. It requires only 2 wires, one for transmitting data and one for receiving. It allows embedded microcontrollers to securely and efficiently pass packets of data back and forth using minimal hardware. Finally, we have PWM, or pulse width modulation. The crucial point is that digital microcontrollers can only output strict binary voltages, like exactly 0 volts or exactly 5 volts. But what if a motor needs, say, 2.5 volts to spin at the right speed? Well, the PWM controller solves this by rapidly flicking the 5-volt power on and off. If it keeps the power on exactly 50% of the time, which is known as a 50% duty cycle, the resulting average output successfully simulates that intermediate 2.5 volts. It's just a brilliant digital trick to achieve analog control. We've journeyed all the way from the outside right into the microscopic architecture of these amazing devices. So I want to leave you with a final thought-provoking challenge. Just look around you right now. Take a glance at your appliances, your electronics, maybe your thermostat. How many hidden brains are silently executing code in your room at this very moment? Embedded systems truly are the invisible architecture of our modern world. Thanks so much for joining me on this explainer. Keep observing the world around you, and I'll catch you in the next one.